We want the membrane to be very thin and with very high mechanical properties. So this is what we observe here. This is the spectra of only PVDF, and these are the spectra of the PVDF mixed with multi-wall carbon nanotubes. So you can see that the mechanical properties improved. We measured also, as I said before, water contact angle increase, including can fabricate super high liquid membranes with water contact angle higher than 150 by using concentration multi-wall carbon nanotubes up to 0.5. The interfiber space decreased with the increase of concentration of molecular weight of multi-wall carbon nanotubes. Liquid interface of water increased, especially because the maximum pore size is reduced. Effective porosity also is decreasing. So based on all these characteristics, one can expect that the permeate flux using direct contact membrane installation should be decreased. So this is what we have observed. However, the membrane here prepared with 1 hour electrospinning time, they exhibit higher permeate flux, but low separation factors, because the membrane has loose structure, it's not very compact. The other membranes, you can see here that we can get very high separation factor. It's 99.995, all of them. So it's very integrated, and the fibers are very fused together, leading to get the concentration of the permeate lower down to 3.6 microsiemens per centimeter, which is very good. And using this type of membrane 5 hours or more. So mainly this is what I want to tell you today, and thank you for your attention.
Very interesting. For nanoparticles, you are selecting some special nanoparticles, nanoparticles such as titania or other alternatives that will increase the hydrophilicity actually, so that will decrease the hydrophobicity.
Okay, so in our projects regarding polysulfone polytetrafluoroethylene, we looked at increase the hydrophobicity of the membrane, but we didn't take into consideration the other nanoparticles that decrease the hydrophobicity. So our main goal here, because we want to use this membrane in membrane distillation, so as I said before, the hydrophobicity should be high. But if you use, for example, nanofibers with nanoparticles that are hydrophilic, so in this case you cannot guarantee that you can measure the water contact angle. You can get water contact angle higher than 120, 130. This doesn't mean that your membrane is adequate for membrane distillation, because when you measure the water contact angle, air is trapped within the fiber, and normally this is like it's not very, very hydrophobic, let's say, because liquid interface of water is the most important parameter here, and we should look at the fiber space also. So we started the use of hydrophilic nanoparticles. So what we want only is to use hydrophobic nanoparticles.
Such as
polytetrafluoroethylene.
And for the carbon nanotubes, you are increasing carbon nanotubes up to 5%, so that will increase the thermal conductivity,
Of course.
and which is opposite of the goal.
Yes.
So,
Yes.
so that
Okay.
increases the strength, but it will also sacrifice that.
Yes, I agree with you. When you use multi-carbon nanotubes, in this case, the thermal conductivity is increased. But the problem here is the void volume fraction, which is very high. So when the void volume fraction, even if your polymer its thermal conductivity is high, the high void volume fraction will compensate this worst effect of the increase of thermal conductivity.
So there is experiment for that one that prove
There is
the experiment to prove it.
experiments to
Yes.
prove that the thermal conductivity increase.
Yeah, it should increase
Yeah,
and also
okay. The thermal
increase and also the flux will not affect.
okay. The thermal conductivity of the material will increase. This doesn't mean that the heat transfer through the membrane will decrease, as I said before.
Yeah.
Because you have void volume there.
Yes.
inside. If the void volume is high, then the heat transfer, if you calculate the thermal conductivity of the whole membrane, not only the material, the whole
Yeah.
membrane, if the void volume fraction is high, so in this case, the thermal conductivity of the whole membrane is not, the increase is not that much.
So I mean, there is experiment to prove it
Experiments to measure the thermal conductivity.
for all, just to compare
Yeah,
between
we
the
can
two
measure
factors.
this, okay. Normally, in our lab, we measure the thermal conductivity of nanofluids. For example, polymer solution or any liquid, any like paraffin, whatever, you add nanoparticles there and you can measure the thermal conductivity in case of your sample, liquid samples, I mean. But for solid samples, like the membrane, also there are some like parallel plates, and also we do this experiments there, but we didn't measure them because what we normally do in order to determine the heat transfer by conduction to the membrane through some models. Yeah. This is, and after that, you will determine the thermal efficiency of your system. This is the most important thing. When the quantity of energy that you apply to your system, what quantity is used for mass transfer, and the other quantity which is lost by conduction through the membrane. So we developed some theoretical model, and we can determine the efficiency and also the thermal conductivity, the transfer by conduction through the membrane. So this is not a problem. We have developed there, including in one of the papers that was published last year, we can find that thermal efficiency of this type of membrane is very high. So it doesn't matter if you increase the thermal conductivity of the material, because we are talking about 0.5%. So the increase is not that much, because they are well dispersed there. And anyways, the increase of the thermal conductivity, when you use nanoparticles with high thermal conductivity, I mean, the increase of thermal conductivity of the matrix incorporated nanoparticles is an issue which is controversial issue. Some scientists said, okay, it may increase too much, but others no. And the increase, for example, when you add 0.5% of nanoparticles in a matrix, the increase may be 10% or 20% maximum.
So and also the addition of nanoparticles or copper nanotube, so there is a limit actually. So if you increase it more, so the membrane will also be very weak.
Yeah, okay. The problem here is you should prepare well dispersed matrix, nanoparticles inside the matrix. So if it is not well dispersed, then you will have the weak points and the mechanical strength will be lost. So the fibers that we made will not have a good strength. Yes, the problem here is to prepare very well dispersed nanoparticles inside the matrix.
Any questions?
Yes, Pratik. As you said about the dispersion of the nanoparticles in the matrix, it's the issue. So how did you overcome this issue, the dispersion of the nanoparticles?
Okay, how you can figure out if your let's say nanoparticles are well dispersed?
Yes.
Okay, the first thing is when you prepare what you want, your matrix, you can like leave it. Best way or simplest way is to leave it some time. Let's say 1 week or something like that, and see if there is any agglomeration or aggregation between particles. But you can use also UV spectra. You put your sample and you check it from time to time and see if it is well dispersed or not. So this is our other thing, which is just you prepare your sample and use it and check the mechanical strength. If the mechanical strength are improved, so in this case, this means that you have well dispersed particles inside your matrix. So,
So concerning the nanoscale, we're talking about nanoscale of the fiber itself, and the nanoscale in the distance or between fibers is no longer nano. I think if I figure out.
yeah,
We're
okay.
talking about few microns. So that's one thing. And then how can you ensure, it's perhaps something like this question, how can you ensure homogeneous distribution of these pores, what we say, from
Yeah.
one sample to another,
Yeah.
you may have, I don't know, deficiencies. One sample is well distributed, another sample, you have more porosity in one side and less porosity in. So how can you control, the quality of your distribution, the pore size of the spaces between fibers?
Yeah, I understand the two questions. The first, to respond to the first question, meaning nanoscale means that we are talking about dimensions ranging from 1 nanometer to 100 nanometers. Yeah? So in this case, when you fabricate nanofibers, you can fabricate nanofibers below 100.
That concerns the size of the
The
fiber.
size of the fiber. So this response, and also this response to your question, first question, and also when you add nanoparticles, the nanoparticles normally mixed matrix membranes belong to the nanotechnology. So this is your what's respond to the first question. Regarding the second one is about the second question about the homogeneity of the void space.
Yeah, that's
Okay,
the
you
problem.
cannot control it because you are in this case. You cannot control it. You have not uniform, but you have distribution of the interfiber space. The results I reported here are only the mean value of what we have